So, hello everyone, also welcome from my side. I'm happy today to talk about our latest addition to our toolkit, which is namely chemical space docking. As you can see, has a registered symbol here, which already gives you a hint that we are not only the pioneers, but the leader in the field. So we're going to see how we can explore these trillion-sized compound collections that we've spoken extensively about until now, but directly in the binding site. Without further ado, the agenda is going to be me giving you a brief introduction. We're going to see how the chemical space docking, or for the sake of time and convenience, I'm going to refer to it as CSD. So we're going to see the workflow, how this is technically possible, so the technical setup. We're going to see how it compares to standard docking approaches. I'm going to share with you some success stories. Then we're going to just dive into our very pleasant graphical user interface for a demo, and we're going to wrap it up with a summary. So before I start talking about that, we've heard a lot about chemical spaces, how they compare, thanks to Alex, to enumerated libraries, how we can search them. So now I need you to take this concept and this paradigm shift of combinatorial chemical spaces and apply it also to docking. Basically, the underlying concept, the basic principle of docking applies also to CSD. So what we're going to do is generate poses for ligands and score them within the binding pocket. In our platform, what we use for docking is our algorithm FlexX, and for the scoring, we have our award-winning dissolution-aware algorithm, which is called HIDE. But why is different? Because when we dive into the millions or even billions or trillions of compounds, then standard docking simply becomes unfeasible and, so to say, unmanageable. Therefore, CSD is a game changer because finally it enables the screening of these trillions and more of compounds while dynamically generate them during the workflow and providing you only with the better scoring one so that you're not overwhelmed with millions of poses. And we do so with minimal computation. But let me show you how. So in a nutshell, we refer to chemical space docking as the next generation of structure-based drug discovery, exactly for what I've said now. We can finally, after many years, access these combinatorial trillion-sized chemical spaces, and we can do this on standard hardware. So we don't need big clusters, GPUs, or even cloud resources and supercomputing. Why and how would a CSD workflow allow you to do so? The first step in a everyday CSD workflow would be to select the chemical space of interest, the one you want to work with. And as we have seen until now, one of the ingredients of the chemical space, the main ingredient, I would say, is its building blocks. And what we do, it's exactly that. We dock only the building blocks. And the major advantage, the key advantage of doing so is that we only dock the smallest percentage of the entire chemical space, and we focus on those symptoms that are actually suitable for following up without wasting time and compute resources on unsuitable candidates. Next, we check for chemical compatibility of building blocks with one another. This is based on reaction rules, as we explained already. And after different steps of manual and visual inspections, we can then proceed into extending them and growing them into larger molecules. If the situation, the project, the binding pocket allows, we can reiterate this process through a second extension step and even more. But let's look a little bit more in detail. We will see that live in the demo in some moments, but just to show you how it will look in the graphical user interface. So basically, the step that I described, the first step of the docking of syntons, it's something that in CSAR we call the anchoring. And this is where exactly the expertise of the researcher really comes into play and shines. Because after the docking of these syntons in the space is done, then it comes in your hands, and then you can really select the best suitable candidates for following up and growing further. One of the examples would be, as you can see here in light blue, This would be the growing vector of the symptoms. We see it here, and we see it also here in the extension. So one of the first things that the researcher would do would look into the direction of this growing vector. For example, it would be absolutely pointless to grow a fragment or to grow a symptom that points towards a dead end, that points towards an area where it's not accessible in the binding pocket, or even worse, maybe points towards the solvent. No one would ever want that. At the same time, to even guide the process and what to say, to keep key interactions, we can also apply pharmacophore constraints to keep key H-bond network interactions and so on. So the process can be guided, and the visual assessment and manual assessment that we do later allows the user to really put its expertise into play and select those anchors that really are meaningful. After doing that, as we said before, thanks to reaction rules and chemical compatibility. Then we move to the first extension, and you can see that we grew some of those anchors into a little bit larger molecules. Once again, there is a visual assessment and filtering of the poses, and we can proceed to a second extension and so on, like I said before. And all of these steps, there are different intervention points for the users. And most importantly, the results at the end are going to be synthetically accessible for you to synthesize, or even better, to purchase, since these spaces included already in our platforms come from compound vendors, which are the leaders in the market. Okay, so this seems absolutely amazing, but how did we at BioSolveIT made this technically possible and to turn this concept into an actual product? The backbone of it is the crosstalk between the two main platforms that are part of this tool, which are CSAR and HPC. And basically what happens is that HPC here on the left works on the server side and takes care of the, let's call it heavy lifting. So everything that is the computing, the orchestration of jobs, handling of these big chemical spaces, and the overall managing of the entire workflow. On the right, on the other side, CSAR operates on the client side. And this is where it's a very interactive environment where really there is a place for the scientists to look and assess the binding site, set up the docking experiment, do the visual assessment of the output. And these two platforms talk and communicate through what we, from now on, we call the space docking mode. So basically, CSAR initiates the computations in HPC, and HPC, on the other hand, provides the process results. This separation allows for the researcher to really focus on the modeling and on the decision-making process rather than on the computational heavy work, which is taken by the HPC platform. So what makes this setup really valuable is its scalability. So HPC, as I said before, and as has been mentioned also by my colleagues, is the scalable vitreous cleaning workflow environment. So it's our way of handling these big chemical spaces in an effortless way. But from the perspective of the user, this is very simple, as we can see here on the right. In fact, after you select the chemical space of choice, which is remotely stored, the entire process that we described until now can start with a single click. After the docking is finished, you're not overwhelmed by millions of poses, but only those top scoring ones are going to be downloaded into CSAR for you to visually assess them on your local machine. What's remarkable also to notice here is that it can run on your own hardware. So from, let's say, the cybersecurity perspective, it's very strong, and there is no need to share your data with third parties or service providers. One last mention of HPC is that it's not only a computational engine, a computational powerhouse, but it also comes with a very clean administrative dashboard that allows the administrators to really handle not only libraries and spaces, but also users and the workflows. So we are not only talking about computation, but also job handling and orchestration, so that everything in terms of big docking campaigns can be taken into account. All right, it's all fun and games. It sounds like a beautiful fairy tale until now, but you would ask yourself, why would I go from my standard traditional docking approaches to your CSD and to chemical space docking? Let's see if I can convince you. So the standard virtual high throughput screening starts by docking a huge number of compounds, like is shown here in orange. And you could dock them one by one, although only a few of them will give good scoring, good docking scores. If we look at chemical space docking on the other end, which is depicted here in green, it gives you the possibility to have a larger pool of high-ranking molecules at a fraction of the time. So not only you're going to be presented with synthetically accessible, high-ranking compounds, but also this is a sustainable process. That's why we like to refer to it as green computing. And with the climate change and everything that is happening in the world right now, I think this cutting down costs in terms of time and computation resources is a big advantage, other than money for sure. And if I couldn't convince you like this, well, we proved it. Actually, one reviewer of one of the publications that I will show you later asked us to make this comparison. So we compared 1 million results from standard brute force docking and CSD. As you can see here, we have big compounds that were docked using brute force docking, so a standard approach, and the overwhelming majority of them results in poor binders. If, on the other hand, we look at the distribution of the chemical space docking depicted here in light blue, we can see that the chemical space docking sample is highly enriched in good docking scores, and we trimmed down those poor binders from millions to a few hundred. So we could retrieve very fast chemically diverse chemotypes, and especially those with good docking scores. So definitely chemical space docking is scientifically efficient, but not only. It's also computationally scalable and exactly computationally efficient. As we can see in this other graph here, if we look at the x-axis, we have the number of molecules up to billions, and on the y-axis, we reported the computation cost in terms of cluster days, and it's scaled up to 1,000 CPUs. If we use standard docking approaches, like here in red, yellow, and green, even when the docking of a single molecule would take 0.1 seconds per compound, 1 second or 10 seconds, this seems nothing if we're talking about a single compound, a couple of them, maybe 10, or a bunch of compounds. But when we dive into millions or billions, then this computational cost explodes massively. And that's why standard docking approaches often require supercomputing resources. And not only, they still take weeks or months to finish. If we now look at chemical space docking, again in light blue here, well, then it stays quite flat, which means that we can, since we dock only the building blocks and we grow them intelligently during the workflow directly in the binding site, we can achieve good scoring compounds at a fraction of the computational cost of standard hardware. And this is why, once again, it's a game changer. So it is scientifically and computationally efficient. And this also goes hand in hand with how fast it is. We did this case study with Enamine's real space. Bear in mind, this was done when Enamine was just, and I want to put just in quotes, 76 billions. It's news from 3 days ago that it's now 83 billions, so even larger for your own information. And we did this on 9 computing units for a total of 60 gigabytes of RAM and 288 cores in total. And here we see the different steps that I already showed you before to just trim it down to the most important data points here. The anchoring with 3.7 million compounds then required only 9 hours, just over 9 hours. From the anchoring of syntons, 100 of them were selected for the extension. This was for 8 million compounds. And of course, this number of molecules required quite some time to be docked again. And we were again towards 31 hours. Once the selection of molecules was trimmed down to 50 fragments, we are back to 1.7 million compounds. And then we are again at 9 hours. The takeaway message from this slide is not all of these numbers, but just that we can really explore a subset of enamine's real space in hours to days on standard hardware. And this is a massive accomplishment in the drug discovery world. Now, I want to show you a real-life application of CSD. Of course, please bear in mind that we at BioSolveIT have conducted successfully over 30 chemical space docking campaigns, and our customers are currently using actively the tool to explore new projects. But the majority of this information, projects, and outcomes are still very confidential. So the only thing that I can show you today is 2 published use cases, which were acting as a proof of concept for the suitability of chemical space docking of delivering good results and good hits in a very short time. The first one that I want to show you is this one that we published in collaboration with Crystals First. And we started from a fragment that was crystallized in protein kinase A, and it was used as a template to screen real space. Among the 93 synthesized compounds that came out after the CSD approach, 40 of them resulted in active compounds, so we had a 43 hit rate. The best follow-up of the fragments displayed a 30K almost fold gain in affinity. We could obtain actually 6 crystal structures from these compounds, and the very striking information from this is that the entire process from hit finding to testing took only 9 weeks. If here we started from a crystallized fragment and used it as a template, different case was this one that we conducted in collaboration with Genentech. Here, the target was a ROC1 kinase, and we tried to find inhibitors. And again, the real space was sampled, and out of the 69 purchased compounds, 27 resulted active with a Ki value below the 10 micromolar. So we had, again, roughly 40% hit rate. We had 43% there, 39 here. So we are on the same level. We especially found novel chemotypes, and this is very important that you often generate novel chemotypes, you find novel IP, and there is a high chemical diversity in these chemical spaces, just by design because they are so big. Most importantly, 2 crystal structures were obtained, and they were in strong agreement with the originally docked poses. So that was also a very solid statement. And speaking of ROC1, this is what we're going to use for our demo. And before I dive into the demo, I have to make a small digression into what we're going to use, because, of course, for the sake of time, I'm not going to use those vendors spaces, but we created a test space for ROC1, looking at what binds in the regions A, B, and C of ROC1. And for every region, we looked at building blocks that could either be known binders, so known to bind, or unconfirmed ones, to give a little bit of diversity. And these made up a chemical space of 1,000 entries of 5 confirmed and 5 unconfirmed building blocks each area. So now let me jump into Caesar. We're going to have a live demo. This is how your graphical user interface will be once you open it up. As you can see, we have a nice search bar up here. I'm going to use the PDB 5KKT, which is a Rock1 crystal structure, of course. And now it's downloading directly from the PDB. I want to do the entire process with you guys live to show you how fast it is. And we are presented with both chains because Rock1 is a homodimer. This specific crystal structure is crystallized with this azindole thiazole piperazine inhibitor. For the sake of clarity, this inhibitor is not present in the test space that we created, and this will give us the opportunity to really see if CSD is able to retrieve key binding motifs without having the solutions preloaded into the test space. This is not a Caesar demo, so I'm just going to be a little bit fast here. I'm just going to tell you that the GUI asks us to select the ligand we want to work with, and this is needed to tell the system what I want in my binding site. So everything in the surroundings of my ligand, not only the residues, but also cofactors, waters, and so on, will be considered part of my binding site. I will then extract this ligand. And again, you saw how fast it was. I'm going to zoom in, and here we go. You see also that the ligand now presents some spheres around the heavy atoms. Some are green, some are red, some are bigger, some are smaller. This is due to our scoring function hide. Once again, for the sake of time, I'm not going to dive too much into it. Just bear in mind that as easy as it goes, green is good, red is bad, like a traffic light system. And we can, if you have questions about it, we can maybe rediscuss this at a later stage. I just want to clean up the view real quick because I don't like to have it so crowded. I want you to focus your attention, because we're really going to chemical space docking, that of course this is a kinase, right? So it presents a hinge binding motif, most likely this azindole, of course. And it mimics those patterns, acceptor, donor, acceptor, that we see in ATP. And as you can see here, for example, this amino acid here, I'm just going to label it. Everything I'm doing very fast is just for the sake of time. Every click can be explained, of course, if you have questions. And we see that the carbonyl in the backbone of this glutamate acts as an acceptor of this H bond that comes from the NH of the azindole. And this is, for example, a key interaction that we would like to keep. And we could use it to guide our chemical space docking, for example. I would like also to turn on the visibility of surfaces, because this will allow us to really look into the directions we want to give to the fragment growing later on. I'm just gonna, again, go real quick into doing some bits and tricks like toggle transparency or changing up the colors, just again, only for visualization purposes. I don't like this green, so I'm gonna go with pink, because why not? And so we can see already that this goes towards the external part of the enzyme, towards the solvent. That said, this was just, I wanted to give you an overview of how the crystallized ligand will look like, so that now we can go into the space docking mode and really work with it. Okay, as I said before, the first step would be to select the chemical space. This would be here. Of course, the spaces needed to be preloaded in our HPC dashboard. In my case, I only loaded the test space, of course. Once I select it, you see that we have a green check mark, and now also the button to start the chemical space docking became green as well. Once I click on it, I am presented with different options. I'm just going to keep this glutamate here because maybe it's interesting for us to see if this interaction is kept. As I said, we could define pharmacophore constraints from this button. We can fine-tune our search in terms of number of poses per symptom that we want, the clash tolerance, allowed ring conformations, and so on. And you can see that the anchoring step is already highlighted here. The chemical space docking standard version is already greened out. So I'm just gonna start with default settings, just to show you how it works. You can see that the percentage of the completeness of the process is reported here. This will become green after the end of the docking process. As I said before, I don't want to bias this chemical space docking demo, but I could have put a constraint here, for example. I could have, for example, told the system that I wanted this carbonyl in the glutamate to be the donor interaction contact. You can see that the docking is progressing. And let's see, after the symptoms are there, it would be common practice to really look at them and to really look into how this, it usually takes shorter than that, and how really these growing vectors are pointing into the binding pocket. And that's why I turned on the surface and I colored it for the sake of visualization to really see whether we can avoid going into the solvent or whether we can avoid clashes with the actual binding site. Okay, now the docking is ready. I think that's because I'm doing too many things at the same time with my laptop. For the sake of clarity, once again, I'm running all of it on my laptop. This is not going to a server right now. I have a local instance of HPC on my laptop. So this is how fast it is. Once the docking is complete, you see that this becomes green, and also you receive a message that your space docking results are ready. I will download them from the server. And here we go. Now the table is populated with my result from the chemical space docking. Of course, many filtering options are possible. Some filters are already by default pre-selected in our graphical user interface because we want to have a good torsion quality and avoid molecular clashes, both intra and intermolecular. So we can already see, let me just, maybe I can clip the surface to let you see a little bit better. Yes. So you can see already that, for example, this first fragment, which is a pyrazole, without having given any direction to the chemical space docking workflow, he already placed it next to the key interaction points. Then we proceed and we have an aminopyridine. What is this? Azendol. And then we continue with the benzimidazole and so on. And you can see already that we can look at it. For example, these ones that are a little bit outside of my key interaction partners and have this fragment pointing towards the center, maybe are not of interest for me in this moment. We can look at the fragment positioning, at the direction of the growing vector, and also at the chemical diversity. Actually, something that we could do is applying filters, for example, for molecular weight. Since we're talking about very, very small fragments, maybe we want them to be below 200. And we can apply this filter once again. And so that we have only those fragments that are below this molecular weight. One other filter that we could apply, and that it's usually used to select good anchors in our good practice, is that we can look into the number of H bonds. We usually want a good number of H bonds because it makes the pose more reliable. Let's say that we want at least 2 H bonds. And once again, we apply the filter so that we, as you see, the fine tuning after even before and after chemical space docking has occurred, are endless. Like we can do, the possibilities are endless to really fine tune and really skim down to those compounds that are really relevant for you. Once again, once we are satisfied with the filter and we look at it in 2D and 3D and we look at the direction of the vector, we can start populating the table here. Everything that will go in this table below will then continue into extension step 1. And you see that now this became populated. We can, for example, this one also creates the right connections. And I like the positioning of the growing vector. This is also cute. And we can continue like that. We can maybe do something even more different. Let's see. Then all of this is I don't like because they are outside of my key area. This starts looking already nice with this benzamide, which is a little bit different than those nitrogen-containing heteroatoms. So I can select it. Okay, I selected 5. I think that for the sake of the demo, those are enough. And I can proceed with the extension step 1. Usually the extension step takes a little bit shorter than the anchoring because we proceed template based. So we take the docking already made of the anchor and we template based the new molecule on top of that. So it takes, of course, template based docking always takes less than regular docking. And we will see that from now on, we could extend the molecule from another fragment. And once it's done, we can proceed with the extension step number 2. And it's important for me to tell you already that molecules were ranked according to the ligand efficiency, because we, in our experience, found out that this is the best. Done. View results. Okay. Before I move on, let me remove the filter of the molecular weight, because now molecules are a little bit bigger and we don't want that. We maybe want something that is beyond 200. So once again, we remove that. Okay, and we are back to the extended results. Oh no. Rank them according to the torsion. And every time you re-rank, of course, you're gonna work towards those molecules. So we can rank them according to estimated affinity, but as I said before, we prefer to rank them according to ligand efficiency, because sorting them according to only one parameter bias the decision. Okay, now we're back, and we can see how they start being extended into bigger molecules and bigger and larger molecules. This one seems decent. This one can be also good, but it's going a little bit too much into the solvent. Let's select, for example, 1 for later. We can have a look. Also, the system tells me that it can grow in either or direction. So this is a visual cue, again, because we really care into the scientist's expertise to make the right decision. For example, let's have a look. This is nice. This with the thiophene is also pointing towards an area where we want other interactions. Let's see if we can get a little bit more chemical variability here. This is nice with the furan that also picks up another interaction with this amino acid here, with the NH of this other residue. So maybe this is nice to proceed with. And also the linker points towards another area, interesting area of the binding pocket. And then we can continue. For example, again, the furan, the points in that direction may be good. How many I have selected? I guess 4. That's also good. And we can continue for extension number 2. Now you will see, as I said before, we ranked compounds according to ligand efficiency until now. Once the molecules are somewhat complete after extension number 2, they're going to be ranked according to estimated affinity. Our estimated affinity is based on the HIDE scoring that I mentioned before. So our scoring algorithm that takes care of two main parameters, namely the hydrogen bond network and the desolvation that you unavoidably pay once you remove water from the binding site to place a ligand. So both the protein and the ligand would, let's say, pay a penalty for the desolvation or make up for it with new interactions. Now the docking is again in process. You see, everything is at the click of your mouse. There is no big computation, big coding underlying. You can do everything. If you are a bench chemist, you can do this. I am a synthetic med chem by background, and I'm doing it on my laptop. So this is really, this can go from heavy chem informaticians to bench chemists without any problem. Let's see if the docking results will be ready soon. In the meanwhile, we can already have a look at this hydrogen bonding network. I can already tell you, I gave it for granted, I didn't explain it, that these the results are here, that these dotted lines depict the hydrogen bonds. So the darker the green, the arrangement, the better the geometry of those atoms involved in that specific interaction. We are now presented with different, let's say, final molecules. And rather than analyzing them here, let me push them. This is our BioSolveIT Lang into the analyzer, which is the better mode we have to really fine tune our search and to really look into compounds. The first filter I'm going to apply is to group molecules, so that for identical molecules, only those with the best estimated affinity are going to be kept, and we don't have duplicates, given that we generated different poses. Now, something that I also want to have to better assess them right now and to show you is to have the crystallized ligand also into the analyzer. Again, I'm going a bit fast for the sake of the demo, but for questions into what to click and what not, feel free to ask. I'm just gonna change the color of these maybe to turquoise so that we have it and have it in 3D. And I'm gonna rank them according to the estimated affinity. So this is the crystallized ligand. And as you can see in beige now, maybe I can also turn the surface down for a second. Without biasing it or influencing it or putting any constraints, CSD already provided suitable candidates that somehow overlap and have a similar direction of what the crystallized ligand has to offer. Some of them, like this one, like I said before with the furan, pick up also for additional interactions that the original crystallized ligand was not able to make. So maybe this would be a suitable candidate for following up to even expand more or to potentiate the ADME properties of the original compound. Maybe you can merge, do structure activity relationship hop into this other scaffold. And again, the fine tuning is endless, and you can continue selecting different properties and different filters according to what you prefer and what are the goals of your project. Since time is running out, and I hope there are going to be also questions, let me just sum it up. I hope I gave you a good summary and a good demo of what CSD is about. Once again, CSD is so efficient because despite diving in the trillions of compounds, we dock only a fraction of it at the beginning, and we expand intelligently from then on, and we still cover the full chemical space. We have active intervention from the user where the creativity and expertise can really shine. Therefore, the assessment can go beyond only the docking scores and numerical values. We can unbias the docking with real symptoms and use the extension vector. At the same time, we can apply pharmacophores constraints when needed. If you have a co-complex ligand, like I showed you in the application with crystal first, Those can be used as templates to enrich promising candidates. And most importantly, everything is synthetically accessible, even more purchasable. If you want to just give it a try or get started, we put together a CSD starter package, which is downloadable from our website, where you will have the good practice to really select the good anchors and how to grow and so on, the HPC deployment guide, the CSAR guide, and the ROC1 test space. And with that, I thank you for your attention, and I hope there are some questions.